So we have our max. We didn't have any maximums. We had our minimum, increasing, decreasing. So now we need to do our concavity, which means we're going to be looking at the second derivative. So I'm going to look at this f prime that we looked at earlier and we worked with, and I'm going to find my f double prime. Okay. So second derivative of 4x cubed will be 12x squared minus 72x plus 96. And then we need to solve that, equal it to 0, so that we can figure out where it's going to have concave up and concave down. So I would first, to solve this, divide everything by 12, because I'm pretty sure everything's divisible by 12. And that'll make things a little bit easier, so that we have x squared minus, what is 72 divided by 12? 6. And then 96 divided by 12 is 8. Awesome. Equal to 0. So then to factor that won't be too bad, because our leading coefficient is 1, and we don't have to do our rational zeros that we're having to do on the previous two steps, because it is a quadratic, so it's a lot easier to do. So we need to ask ourselves, what multiplies to 8 and adds to negative 6? Negative 4 and negative 2. So I'll have x minus 4 and x minus 2. We use the zero product property, set each part equal to 0, and I'll be left with x equals 2 and 4. And so those are the numbers I'll put on my number line. So pick some values to test. Let's do 0, 3, and say 5. And we're plugging these into our second derivative, but let's plug them into the simplified second derivative, because that 12 that we factored out and divided, it's not going to change its sign. Okay, so I'm going to plug in 0, and I'm going to have negative 4 and negative 2, so positive. So it's going to be concave up and happy. Plug in 3, and I get negative 1 and positive 1. So it's going to be concave down and sad. And then I'm going to plug in 5, and I will get positive and a positive. So happy. So we will have inflection points. I'm going to abbreviate that like that. At 2, comma something and 4, comma something. Those happen when it changes from happy to sad or sad to happy. And it has to exist there, but it's a polynomial, so it does exist everywhere. Okay. And then we also need to do our concave up intervals and our concave down intervals. Okay, so if I plug in 2, I have to go plug it into the original equation, so that x to the 4th minus 12x cubed plus 48x squared minus 64x that we had originally, we plug in there to get our output. So when I plug in 2, I'll get negative 16. And when I plug in 4, I get 0, which makes sense, because if you look at 4, my y value was 0. It's an x-intercept. So we've had that point twice. Concave up starts as far left as what value for my interval? Negative infinity. And it stops at 2. And then it'll go on to be positive or concave up at 4 and goes all the way to infinity. Awesome. And then a concave down, it is only sad from 2 to 4. So now let's zoom out. And we have all this awesome information. It is zooming ever so slowly on its very own. Okay, I want more. Come on, man. Oh, there we go. Oh, not that much. Okay, so I am going to draw my coordinate plane here. Kind of use that to help me out. And we have all this useful information. So let's start with our x-intercepts. And we have x-intercepts of 0 and 1, 2, 3, 4. And then we have y-intercept of 0, and that's already marked. And we have no asymptotes. We have none of that. So that's all we have from our algebra. So algebra was not super helpful in getting shape of this graph, like sometimes it is with those asymptotes. But now we can do a minimum, and it's 1 and negative 27. So I am going to just, let's go by 5s. How about that? So then you can do that. So 5, this will be negative 5, 10, 15, 20, 25. So we can go by ones. Since I'm going by something different, I need to label that. But you can change. Your X's and Y's don't have to go by the same thing. As long as you're consistent, it's labeled. I can see what it's going by. Okay. So then I have a minimum of 1 and negative 27. So it's going to be a little bit past that. So there's my minimum. I don't have a maximum. We do have some increasing and decreasing. I know it's increasing from 1 to 4. So it's going to have, I'm just going to dot it. It's definitely going up there. Okay. And it is also increasing from 4 to infinity. So it's going to continue to go up. Okay. But then it is going down from negative infinity to 1. So it goes down all the way through that intercept and down. So it looks U-shaped now. It's not actually U-shaped, but it looks U-shaped as it is right now. We do have some more points. Inflection point at 2, negative 16. So that'll be a little bit past that 15. So we'll have to go through that point. And then our 4, 0 that we already have. So concave up and down is where it actually will help take shape. So it is concave up, meaning it is curving upward from negative infinity to 2. So that means it's actually going to be, oh, I didn't mean to do that. It kind of jumped on me. It's going to be pretty U-shaped all the way to here. Okay. It's almost like part of a parabola to that point because that's concave up. But then it's going to be concave down, which means it has to have somewhat of a downward curve between 2 and 4. So it's going to have to curve in a negative direction there. And then it's going to come back up and be happy, concave up, here. So you have that goofy looking graph. And if you graph it in a graphing calculator, that's actually what it looks like. It's very odd. All right. So watch that concavity. That's where it really finally finishes out and takes that shape. Because otherwise, it kind of just looks like a parabola before. Any questions on that? Okay. Last bit. Okay. So we have the graph of our first derivative of the function f on the interval negative 1 to 8. And it is shown. So we're just looking at it on that domain. Okay. So it is the first derivative. Okay. This graph is the first derivative. And so some of you guys had asked me questions over the weekend about that. When you are looking at analyzing graphs, if you're given say the original function and you're wanting to talk about the first derivative, you're going to be looking at the increasing, decreasing of the tangent line. So it's almost like if you were to trace it with a bunch of little straight lines, when are those slopes positive? That's where your first derivative is above 0. When are those slopes negative? That's when it's below 0. When are those slopes horizontal? And that's where it crosses the x-axis. And that's how your first derivative. Now, you may not know exactly how high or exactly how low. You just know it's below or above. That's about how much you know. And so, again, these are just sketches. They're not exact. All right. So on the interval, when is f increasing? Well, again, f has to be increasing when the first derivative is positive. So all we have to know is, where is it positive at? Well, it's positive starting right here. On what interval is it increasing? Is f increasing? Is going to be where it is above 0. So we have above 0, it starts here, and it continues to be above 0 over here, and it stops at that place. So it would be increasing everywhere it's above 0, and it would kind of stop, and then it's increasing again. Does that make sense? Where your first derivative is positive, essentially what it's asking for. Okay, so on what values is f increasing? It is increasing from, what is that, negative, would that be negative 6? All the way to 3? I need to erase my stuff. Now I can't see over my own point. Yeah, 3. And then from 3 to 8. It's not increasing at 3. 3, it would be equal to 0. Okay, does that make sense? So you're just looking at where that is above 0. All right, on what interval is f concave down? So when is f concave down, it's talking about the second derivative. All we have is the first derivative. Okay, so if you're looking for concave down, you're looking for the slope of your first derivative, okay? Because derivatives are slopes. And so if we're talking about second, I need to slope my first, okay? So if I look at all the slopes on this, I'll end up having to erase this. Of all the places that slopes happen, they're all going to be positive up to a certain point, and then they're going to start being negative. That negative slope of my first derivative is going to be affecting the concavity for my second derivative, okay? So I'm going to be looking from, erase that, from just that slope there, where it is going downhill is where my original graph that we don't have, where it's going to be concave down. So it starts that, if you look, it has a point here, so at 4, and then it starts and goes down here before it changes. Okay, so those will be your max and min. Well, it's also going to be your points of inflection at this point too. So your max and min of your first derivative are your points of inflection for your second derivative. Okay, so then it is concave down starting at 4, negative 4. And then it becomes starting to go back up at 3. So you are concave down there. Any questions? Do you guys see that? So sometimes they give you the original, and I think the ones in your homework, I want to say on some of them they said give the original, and they wanted you to sketch the other ones on top of it. I think it was a thing they did on your homework. All right, so then the next thing it says is that what x values does f have a relative extrema? So it basically wants to know, where does f have a max or a min? Well, if you think about this being the first derivative, the graph of the first derivative, you're going to have maxes and mins. If you think of our number line, that's where we equal 0, and then we test around it. So where it equals 0 is going to be where they have relative extrema. So you're looking at where it's changing from below 0 to above 0. So we can't use this guy here because it didn't change from above to below. Do you see that? So that would be like that stall that we talked about in the original graph. That would be a stall. Okay, it did equal 0, that slope, but it continued to be above 0. But this went from negative to positive. So then that is where we would have a relative extrema. So at x equals, what value is that? Negative 6. Any questions on that? Okay. And then last question, at what x value does graph of f have a point of inflection? So I kind of referenced that earlier, but a point of inflection is going to be when it's changing from increasing to decreasing on the first derivative. Okay, so if we look back at, okay, it was going up here, and then it changed here, and then it was going down here, but then it changed here and went back up. So increasing and decreasing for your first derivative is your concavity. So we know we have points of inflection at x equals negative 4 and x equals 4. Does that seem right? Let me erase my dots. Oh, no, this one should be 3. Okay. Any questions on that, analyzing that graph kind of backwards? The AP test loves this, especially for multiple choice. Yes, Yoli?
How do we get the negative 4 point of inflection?
Right here. So where it changed from increasing to decreasing? Very good question. All right. Those take practice, so you'll see a lot of that.